Uh, there we go. Just clicked record. Thank you for the reminder. You know, as we were all very familiar with, Roger Moore was the head of Intel back in the 60s, and he saw this trend happening, that they're able to fit more and more transistors on their computers as time went on, or on their chips, I should say. But what happened as, you know, we continued into the 2000s, suddenly we started hitting a cliff, right? Where newer processors weren't scaling with the new transistors, or rather their single threaded performance wasn't scaling. And so that's why we've been buying chips that have been 2 to 3 gigahertz for the past 15 years, right? The frequency has plateaued. The single threaded performance as well has plateaued quite a bit. And so with that, we're finding a need to move to a different paradigm. And that's shown here on this graph as well. These bottom checks here are the number of logical cores on each processor. And so while they've been able to keep, you know, cramming more and more transistors on chips, those extra transistors have not been going towards single core performance, but rather towards the ability to have multiple cores. And so not only does your laptop have multiple cores these days, but even just about every single cell phone in your pocket has multiple cores. Your watch has multiple cores. There's a whole host of things in terms of how, you know, how these are, you know, we're needing to use multiple cores and multiple threads and parallel processing in general in order to fully exploit all the hardware we have available to us these days. And so that means that parallelism is required to get our best performance. It's no longer this domain of the supercomputers or the clusters, but you need this. It is fascinating, though, to look at what supercomputers have. But even in our own computers today, we have a single processor core that can do more than one thing at once. Even our processors have multiple cores, you know, and even, you know, standard desktops can have as many as 50 cores all put together in a single computer. And then of course we can network lots of computers together, leverage, you know, the cloud infrastructure to make sure that, you know, we can scale up and down very, very easily. And even beyond that, there's now specialized compute hardware, beginning with GPUs, which were specialized initially for graphics, hence the name, but it was discovered that they have extraordinarily powerful parallel computation processing capabilities that aren't just constrained to the domain of graphics and 3D graphics, but can also be applied most notably towards matrix multiplications, which is the core of a lot of modern machine learning, and a lot of algorithms in general all boil down to a matrix multiplication of some sort. And so being able to do those in parallel is a huge, huge advantage. So those are GPUs, and now they're even more specialized ASICs, or application-specific integrated circuits, like TPUs or tensor processing units, and other fun things along those lines. So like I said, it's kind of interesting to see what the fastest supercomputers are doing. And you can see that this is the top 500 list from this last year. And the #1 computer is a US-based computer in in Oak Ridge National Laboratory. And just kind of tearing this apart, seeing what it has, kind of exemplifies all of these different modalities of parallelism. If you look and see, there are over 4,600 nodes connected all together. Lots of, you can almost think of them as independent boxes all networked together using extraordinarily fast interconnects, sure, but you can imagine them as being separate boxes. Each node has 2 processors, each processor has 22 cores, and in addition to that, all of these nodes have 6 GPUs attached to them. And so all told, this ends up, depending on how you count those GPU cores, you get upwards of 2 million cores available to use, but you need to work within this heterogeneous parallel environment. And so the challenges of working with parallelism here are that we're chasing peak performance. We need a fast language in order to get big benefit. There's no way that Summit supercomputer will let just any language run on it. It needs to be able to use the resources available to it in an efficient manner in order for us to deploy onto that. And the same is true in other situations, right? You don't want to be burning time and money doing, high level language stuff. You want to be programming exactly towards the hardware you have available to you. So we need to reason about and write these programs in parallel, but we learn about them serially. So we need to think about how we safely express our parallelism. And this whole thing, to do large computation, well, that often dovetails with large data sets, right? So you need to think about data movement, how you get your data to the computers that are doing the task. And you have to think about those costs of the data movement. And then, of course, like we've already seen, there's all these different parallel hardware configurations, from multiple threads, multiple computers, specialized hardware, and so on and so forth. So we need to think about what strategy of parallelism that we are going to use in order to exploit this. So, of course, our solution here all stems from the Julia programming language. It is a fast language. It's a language that we can work and optimize in order to make sure that we don't have overhead beyond what's necessary, right? That we can very, very efficiently express ourselves. It's an expressive language that allows us to, talk about these different parallelism paradigms. And so I just want to go over just a little bit, very briefly, what the kinds of parallelism constructs that we have within the Julia programming language and how you would use them, what they look like. And then Alan Edelman will take it off from there and give a more in-depth talk from there. So these are the kinds of strategies that we can think about when we're programming in Julia, and the kinds of strategies that Julia allows us to express. So the first is called single instruction multiple data. And this is the built-in parallelism within a single CPU, within a single core of a CPU, which is something that I think lots of folks don't really think about, the fact that our processors don't really work the way we think they do anymore. They can do lots of things all at the same time. Even just a single core can do lots of things all at the same time. It can be fetching instructions, it can be moving data, and in fact, it can do multiple operations at once. Classic example here is called SIMD, which is a single instruction applied to multiple data. So the example here goes from 4 separate plus instructions to a single vector plus instruction. And the magic in this all is that single vector plus takes exactly the same amount of time as a scalar plus does. And so essentially, by allowing your computer to generate these single instruction multiple data instructions, well, then you're able to get a 4x in this cartoon example here, 4x speed up, or even greater. And so how do you do this in Julia? And the answer is as simple as writing a for loop, right? This is how you write a for loop in order to get these things working as quickly as possible. There's one little trick that you need to know about, and that's the fact that we can't have bounds checking in order to get this working. We need to make sure that bounds checks are off, and there's a really nice macro in Julia called inbounds that allows you to turn off bounds checking, and it makes sure that this SIMD optimization will happen. And that's all that's needed. Julia will automatically exploit the hardware and compile down to exactly the code that you need it to compile down to. And modern SIMD units can be as many as 8 or 16 32-bit floats at a time, which is a huge 16x parallelism is just a great resource. Of course, it's limited to these processor instructions and these things, so it's best for these tight numerical loops. And in some cases, you need to be explicit about the fact that, hey, we can do a little bit of reordering here in this for loop. We're not marching completely from left to right. There, these things. And so the @SIMD macro can allow you to express that additional, decoupling of your for loops. Then there's additional multi-threading, right? So we've talked about how computers have multiple cores, And you want to be able to use all those cores together. And by default, Julia uses multi-threading for its BLAS, its matrix multiplications. You can explicitly do this just by adding an @threads, just kind of like we did with that @SIMD. You just add a threads macro in front of your for loop, and that will split your for loop across all the threads that are available to you. And you just need to start up Julia telling it, hey, these are the number of threads. If you're working within an IDE like Juno or Visual Studio, they automatically start Julia with the appropriate number of threads. So that just works. And new in Julia 1.3, as of a few months ago, we have a revolutionary new work stealing and efficient nested @threads macro. And this is, we call it the parter algorithm that allows us to have multiple nested threads loops that allow you to fully exploit this, not just in your user code, but in libraries as well. And so Julia's standard library, as well as the standard libraries and Julia ecosystem, are starting to use this, because now we have fully composable threading, multi-threading, and allow you to do this. Thirdly is the fact that we can have multiple processes talk to each other. So this could be on the single machine, or it could be multiple machines, all that work together. And I imagine this is, you start up, for example, 6 different Julia sessions. And again, these could be all on the same machine, just kind of like, launching 6 different instances of Julia, getting it all up and running like this. Or it could potentially be in a computer lab, right? You can imagine running around a computer lab, manually typing in at each computer, starting your analysis on, an 1/8 of the data set or something like that. Well, you don't want to manually run around a computer lab typing in all the keyboards. So instead, Julia itself can help you manage this. And this is built into the Julia standard library with the distributed package. It allows you to express these things about, you need to manage, hey, everywhere, for example, I want to use a certain package. So that's, you can imagine it as thinking like, well, I'm running around to all these computers, typing using statistics in all of these computers. And everywhere I want to define this function. But then once all those things are defined, and once we have our processes added, well, then we can just use this, again, just an extra macro in front of our for loop to make sure that our computation gets distributed over all the resources available to us. So there's a whole host of ways of doing this. We can talk about, kicking off jobs, forgetting about them, doing some sort of reduction, or even just returning one value per iteration. And depending upon how heavy of a lift this data transfer is, well, each one of these will have its pluses and minuses, but it's very easy to choose how you want to do this. And it's as simple as a macro or changing your map function to a pmap, for example. Now, with the advent of all these great cloud providers, we actually have access, as us normal human beings, we have access to essentially supercomputers in the cloud. They're just computers that we can use and rent. And so we can manage these clusters, and Julia Computing has been putting a lot of resource into this to allow you to deploy your code quite easily and seamlessly. And so this is the last thing I'll present before Professor Edelman jumps in here and gives his talk. But I just want to show you just kind of how this works in practice, how you can use what Julia Run, and in particular, it combines with Julia Team to deploy your applications. And this is exactly the way it looks here. Let me make this a little bit bigger, just to maximize our space. So the way this works is that you can now, within Julia Team, register your applications, your programs that you want to deploy to a cloud or even an on-premises hardware. We can work with you to install this and get it connected with on-premises clusters. And then once you have that all installed, it's as simple as, we have 3 different production models here that we can talk about and run. And it's as simple as saying, hey, I want to run this particular model in the cloud. It automatically instantiates all the things that we need to do, all those things about running around to all those computers saying, hey, I want to use this package. I want to make sure that all of its dependencies are available. And we want to make sure that all the versions are exactly the same version that we have. So if you're familiar with Julia's package ecosystem, you'll know about these project and manifest files that allow us to have our exact dependencies available to us and have perfect reproducibility of our project. We can choose exactly which version of the code we want to deploy. We can deploy the existing release, or we can say, hey, I'm doing development. I'm doing some sort of interactive development. I want to, know how, test some new code out. So I can say, hey, instead of running on the master branch, let's run on, some test branch that I'm playing with. And we can scale up, say, run this code distributed across 15 workers. We can choose to say, hey, I want these workers to have a beefy GPU, one of these super accelerators attached to it that can allow me to get best case performance out of this. And then it's as simple as submitting our job. And this is a relatively complicated task. It takes a decent amount of time to do. But once we hit submit, we'll get confirmation that our job is successfully submitted to the cloud. We don't need to worry about all the connections. And in fact, Julia Run will even automatically provision resources for us if we would like. And then down here, we get a table of all of the previous runs that we've done. So here's this model that I just kicked off at 18 minutes past the hour. You can see exactly what I'm running. It's the leucine model simulation running on my branch. And you can even find out exactly what Git commit we were on. It's currently running, and that means that I can look at the logs, see what's happening, and it'll go through and download everything, get everything set up. This takes a significant amount of time to run, even on 15 workers. So like any good cooking show, I have a pre-baked version here for you all to look at. And we can go in and look at the logs here, and you can see it's installing all the dependencies and so on. And down towards the bottom, here are results. And in fact, we can print them out. Here you can see it took a decent amount of time. This isn't something that I wanted to run on my laptop. I wanted to use this great cloud hardware. And here are the summary of the results. And in fact, I can go back here and to our Julia team instance and download the results directly as a CSV file that I can load in and start working with. So that is one of the great ways that you can use with Julia Computing and get things running in order to deploy your hardware, your code on parallel hardware. And with that, I believe Professor Edelman is ready to take it away. If you want to, you can unmute yourself and then do a brief introduction and take it.
Yes, hi everybody. I'm Professor Alan Edelman, and sorry that I couldn't arrive 15 minutes ago, but looked like you were in great hands with Matt. Just to let you know, I had to teach my Monday, Wednesday, Friday linear algebra class, which is a class with about 200 students. Today, you might notice today's Tuesday and not Monday. But this is every year when it's President's Day, Tuesday becomes a Monday schedule. And so I completely forgot about that. But I'm here now. Let me see if I can share my screen. Oh, okay, looks like-
I need to stop.
So you have to let go. Thanks, good. And now I should be able to share my screen. And if I share my whole desktop, then I can just, Matt, maybe you can just tell me that I want to bring up this. Oh, actually, here, let's do it this way. Can you see a full screen with the power of language, Matt?
That looks perfect.
Perfect, thank you so much. So what I'm going to do is kind of stand back. I mean, I kind of got the sense of what Matt was doing the last 20 minutes or so. And I would like to give a repeat of a lecture that I gave last November at Supercomputing. Maybe some of you were even there. This is the Sidney Fernbach Prize Lecture, so this is kind of an encore performance from last November. And it was actually in Denver, but then I gave it again in Seattle. So what I would like to do is give you maybe sort of the big picture philosophy of where Julia stands with parallel computing and where we want it to go as well. So it's not only where we are today, but the very problems that we want to solve into the future. And so I entitled my talk, The Power of Language. So what I'd like you all to imagine is I'm at a big supercomputing conference, and I've got an audience of 4,000 people. I never speak to 4,000 people. Maybe I speak to a few hundred, maybe 1,000 was my record, but there were 4,000 people live in the audience. But as you can imagine, 10 people, 4,000 people, after a while, it doesn't even matter. There's no real difference. And I got up there and I talked about the thing that means a lot to me, the power of language itself, the power of computing language. And so I've got my sequence of slides to talk about the power of language for performance, the power of language for productivity, the power of language for impact, for abstraction, for community building, which I think is one of my favorite aspects of the power of language. Code reuse is connected to community building, so the idea that people shouldn't be reinventing the wheel all the time. Even at, professors, we give these students homeworks to do. We have 100 kids writing the same program over and over again. What's wrong with that story? I mean, everybody learns to do it themselves. Maybe that's good, but it's not the real world, or it shouldn't be the real world. So the power of language to engage students is something I worry about. And ultimately, this was an HPC conference, so the power of language for HPC. So if you've ever gone to the supercomputing conferences, to the HPC conferences, you may know that they are given every single year. It's an annual conference, and it's always the week before Thanksgiving. So if you could place yourself in the Thanksgiving mood, next week's going to be Thanksgiving vacation, just to kind of place yourself into the scene. I took an example of a standard social studies project that any second grader might do. Let's compare the past with the present. This is the sort of thing that my kids, when they were little, I remember them doing, the different clothing they wore, how they transported, how they communicated with each other, the games they played, that sort of thing. And I turned that into the week before Thanksgiving, that is the HPC conference, and I wanted to compare the past with the present. And so the supercomputing conferences started, I think the first one was 89, I think my first was 90, I'm not even sure anymore, but I decided to say that my first one was about 30 years ago, which was about the first ones, and then this was the current one, Supercomputing 19. And so I'd like to play this second grade social studies game and talk about the past versus the present. So in the early days, the only thing anyone ever talked about was performance. Performance, 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 performance. It got to the point where it almost got silly. Everything was performance. Now, as we sort of matured and we think about things, we realize that, well, performance might be a component of what we really want. What we truly want is impact. But that's kind of become the more important thing in 2020, 2019 now. In the old days, it was okay for users to report their results, their performance. They got so many teraflops on such a machine, and they would announce it in a conference. Now, what people want, at least in the academic world and in national laboratories and so forth, maybe not so much in private companies, but even there, they want it within their organizations, is reproducible science. The idea is that it's not good enough that somebody could get a lot of performance and then they leave the organization, or in the case of a graduate student, they graduate, and now nobody knows how to work that software anymore. Those days are not allowed anymore. That was 30 years ago, but nobody wants to do that today. In the old days, there was composability. Who cares? Who cares if two bits of software can work together? Now everybody needs it. I used to have I would teach this graduate course at MIT on high performance computing. And this was probably the worst assignment I could ever have given. I'd like to tell you about it. What I used to do was I used to tell people to take a code off the internet, some MPI code, whatever you like, and make it run. That's it. That was part one. Make it run. Whatever code you want, somebody's code, make it run on your computer. These are MIT students. They work very, very hard. They like to get A's. And so they got something to run. Then I said, take two things and make them run together. I mean, I gave the example of invert a matrix and then run a Fourier transform on the same matrix. But it could have been anything from any domain. I didn't really care. The problem was make two pieces of software work together. I'll tell you, I gave that assignment for several years in a row. Very, very few students succeeded. Not because they didn't try, but it was just the nature of the software that we were living with and we're still living with. And so that's not acceptable anymore, that software is just sort of standalone and can't work with anything else. Portability was discussed, but really not taken too seriously. Now people want software to work on heterogeneous architectures. That's the key thing nowadays. Okay, back then, message passing was in its infancy. There was something called PVM in the early days, which grew up to be MPI. Now MPI is very much everywhere, but it's starting to show some signs of age. When MPI first came out, and some of you may know what MPI is, it's sort of the basic low-level parallel computing tool that's been used for ages. When it first came out, people would, there would be these conferences. I remember going to, I was a young graduate student. I went to this conference and I raised my hand. You know, I remember Jack Dengara was there were other people, famous people. And I asked, so MPI, that's not what everybody's going to use, right? That's just like the low-level library writers. Like the main applications will be in higher level software, right? And everybody said, yeah, right. Yeah, no, MPI won't be everybody. And 30 years later, it's still the case that most parallel applications are written in MPI. So back then it was a small, younger community. Now, how should I say it? Students have lots and lots of choices of what to work on right now. And of course, it's always exciting to get the younger folks interested in this field. Back then, industry was mentioned, but now the industrial connections are a bigger deal. And then my final word in my little social studies comparison between then and now. Back then, if you wanted to be successful, you would roll up your sleeves and performance engineer. That was kind of the job you had. Now we have sort of an evolution of workflow for success, which goes to various higher levels. So you can start with libraries, move your way to SDKs. A lot of people are talking about domain-specific languages, like people are doing for machine learning. And then, of course, this part of the space where we sit in is the highest level yet. We want high-level languages without sacrificing any of the key desires that you want for high-performance computing. So let me just do a check. Matt or anybody else, can you hear me? Everything going okay? Hello? Just want to make sure that.
Yes, I can hear you great. I was muted.
You know, it's funny when you don't hear anybody, you always get the feeling that maybe, just maybe, I'm talking to a dead network. But thanks for checking. Okay. Yep. All right, so then to continue. Yeah, so today's subject, of course, is high-level languages. And here's sort of a bit of historical precedent. And there have been some philosophers and mathematicians, and I put in a graduate student working with me because I thought he had something important to say. People have always known back in time, I mean, this is not rocket science, people have always known that language matters. And various philosophers and mathematicians have said it in different ways. But basically, without the right language, there are certain things you can't even express. Poincaré talked about that if you choose your notation and therefore your language carefully, you can do amazing things. Wittgenstein talked about that whatever the limits of your language is the limits of your world. And then Valentin always is amused because he's a graduate student in the lab and a major contributor to the Judo language. And he pointed out that language is really applied psychology, that if it's done correctly, we can actually coax all the good things we want. We can get people to write better code, to have more performing code, even to get people to work with each other and to have composable code. And so, so the point of this slide, and I don't think it's a surprise to anybody listening, but the point of this slide is language really does matter, okay? It's not the case that all languages are created equal. Some will work better for various reasons than others, right? And so what you do really matters in this space. So when it comes to HPC, there have been experiments. Some of them are actually 15 years old. So, and some of you may know about these experiments. There a lot of very good people worked on these 3 high-performance computing languages. Maybe some of you actually tried them. There's Chapel, which is still around. And then there's Fortress and X10, which are pretty much dead, I believe, as languages, or at least as I understand it. But 15 years ago, the US government defense agency, which is known as DARPA, they had a high productivity computing systems initiative. And their goal was to get people much more productive with high performance computing. And so they funded some projects, and these three languages, Chapel, Fortress, and X10, came out 15 years ago. And you could say, well, what did we miss? Because these two languages are dead, Fortress and X10, and Chapel is still kind of hanging in there with Cray and a bunch of, it's got some fans. It's got some very nice things going on. All of these languages have some really nice things. But arguably, it would be easy for many people to say, we tried this experiment 15 years ago, and it didn't really catch on. So maybe it's impossible. Maybe the idea of having a good language for HPC is just never going to happen. We tried, we put money into this, that's it. Okay, I don't want to believe that. And in fact, the creators of Julia don't believe that. But just to kind of map out the history, while I was at the conference, there were these nice set of panels. I actually took a photo of them. Everybody who went to that conference saw the set of panels of all the supercomputings going back to whatever it was, 89 or whatever it was. And then all the way up to last year, 2018 would have been the year before last year. And I went and I read all the words. You can't quite see it on my picture, but I read all the words, and I noticed that starting from the beginning, there was a blurb for programming languages. So various different programming languages were mentioned as sort of like, like the time capsule of where we are in supercomputing. And in fact, from 1988 to 2010, right, so all of these panels going up to, I guess this one would be 2010, all the ones far to the left and up to this one, there was a mention of programming languages with the exception of 2005. But basically, programming languages were mentioned each and every year between 88 and 2010. However, if you looked at the last decade, I call it the dark decade, all the panels from 2011 to 2019, well, or 2018, all of those panels did not mention programming languages. None of them mentioned programming languages. And so you look at that and you wonder, what's gone on? Something seems to have gone wrong. Why in the middle of this conference that took programming languages so seriously up until 2010, right, a whole decade, I call it the dark decade, nothing has happened in this area at all. I mean, how could this be? How could we have allowed this to be? When I was on the stage and I had 4,000 people listening to me, I said, I don't know if one of you are responsible for next year's panel, but if that's you, please put programming languages back. So I don't know if that'll be on deaf ears or not, but I did say that out loud when I was at the conference. So what did we miss 15 years ago? And I'm going to answer. I think that the mistake that was made was that they decided to make a language for high performance computing. They decided that somebody needs to create a language for high performance computing. And what we believe is you need first a good serial language, a good language for serial computing, and then a good multidisciplinary user base so that this could be extended. All right, and so we have all these fancy things, and maybe I'll mention some of these later, or maybe Matt's already mentioned some of these things. But we think of Julia, obviously, because we think Julia has all of the right pieces to be able to have a good serial language so you can have a good parallel language. So in here I brought up some of the universities teaching Julia. I think this has gotten bigger. I just picked a few logos. I mean, arguably MIT, I just came from a class where I'm teaching Julia and I'm not the only one. But it's happening now. So universities are teaching Julia left and right. Okay, and so what is our lesson? Here are the four of us, these are the four co-creators of the Julia language, the Stefan and Viral and Jeff. But now, we have thousands and thousands of contributors that make Julia so wonderful. But we knew that the right user base starts serial and takes 10 years to mature. In fact, believe it or not, when we started this whole project, we actually said, I think it was Jeff himself, this is Jeff right there, Jeff said that there's not a chance in the world this will catch on until 10 years from now. Do we still want to do it? And I'm just going to say patience is a virtue. We said we're still going to do it. This is too important. And if it takes 10 years to catch on, and so be it, right? If something's worth doing, then it's worth doing, and we're just going to get it all started, and we're just going to let the community grow as it did, and it's continuing to do, slowly but surely, right? And we see every year I look back in amazement at how many more Julia users there are this year than the previous year, And then I look also with anticipation and say, but can't we have a lot more? I guess that's next year. All right, but it's growing and we're enjoying that, and we all benefit from the larger number of users. All right, so patience is a virtue, but maybe you all knew that also. That's certainly the motto of the Julia work. Okay, since this was an HPC conference, I pulled out a few people and projects at the national labs. I mean, maybe some of you are on this webinar. I called attention to some machine learning examples, to some traditional scientific computing examples, to Jane here, who runs our JuliaCon, who's on the organizing committee, who's at a national lab, various different projects that are happening all over the national labs these days. Okay, so sometimes people ask us for numbers. Obviously, these numbers are back to when I gave this talk, but they've already grown since October of 2019. But of course, we don't really know. Julia's open source. Anybody can download Julia and not tell us. So we don't really know exactly how many users there are, and I suppose we never will. But we do have certain proxies, and so we have exact numbers, and you can conclude what you like from these various proxies. But we know how many downloads have been initiated. We know how many have gone through the Docker Hub. We know the packages, the news articles, the discourse thread, and so forth. And so, I mean, we actually think that Stack Overflow questions are actually a pretty good measure of use, because the more people use it, the more people ask questions. So, you could take these numbers as you will. These are concrete numbers that we have. Again, they're proxies because we can't tell you how many Julia users there are. But as we certainly see, these things continue to grow exponentially. And so, we're still riding that trend. All right, so now you've got a bit of a background as to the power of language and what we're trying to do. But really, this is just talk until I give a real live demo. And so I'm going to do that right now. I'm going to go over and give a demo, which I call the Julia HPC Dream. And I've done this before at big conferences. It's actually always scary. But I will run Julia this is in a Jupyter notebook. I will run Julia live in front of thousands of people. And I know that the whole thing could die on me live. It certainly has. But I also believe that unless you show things to people live, they don't really believe it. They don't believe they can do it for themselves. So I'm using a Jupyter notebook. I don't know if Matt mentioned it, or maybe everybody already knows about Jupyter notebooks. Here's the little logo. In case nobody's told you this before, these notebooks are everywhere. They let you do reproducible science. The JU is for Julia, the PYT, of course, is Python, and then the R is for R. So I can get rid of these things to give you more real estate. But I would like to give you a bit of a feel for the dream. And so I'm going to give you an example from linear algebra, but there's nothing special about linear algebra. If you like linear algebra, then you can understand what I'm saying. If you prefer other things, machine learning, some scientific applications, just substitute what you like to do for linear algebra, because the idea will carry forward, right? There's nothing particularly special about linear algebra in what I'm saying. But let me get started by saying that if you're doing linear algebra, there are a lot of things that you can use if you just want to run a library. So many of you may know that these days, if you solve a big linear system of equations that's not special, or if you do what's called the singular value decomposition or an eigenvalue, whatever it is that you do from linear algebra, if the matrix is not particularly special, if it's a dense matrix, people use LAPACK. That's the thing that people use. It's the linear algebra package, right? And here is the cover of the manual. But to be honest, people tend to call this from Julia, Python, MATLAB, Mathematica, whatever it is that they're using. Most people don't even know that when they're doing linear algebra, they're doing dense linear algebra, the different packages are not even running different algorithms. They're all running the same LAPACK collection under the hood. So there's no such thing as Julia's linear system being better than Python's linear system, because it's really the same linear system solver. In parallel, there's the scalar pack system, the scalable LAPACK. You see the same LAPACK logo here. Let's see if I can blow it up a little bit if you can see it better. But this is like a 3x3 version of the LAPACK logo. And I don't know whether it's getting a whole lot of use. I think there are some fans, but I think it's kind of also a little bit hard to use, I think. I don't know. but people have used it and happily. And then, of course, another thing is the AR pack, which stands for the All-Nolly package, which is something that people use for sparse linear systems when you have a lot of zeros. But none of this is very important. The key message is that if you're doing something for which there's a library, and people have taken care of, what it is you want to do, go ahead and use the library. Why not? I mean, everybody benefits. You get code reuse, and everybody's happy. But I want to consider the situation where you're not just your everyday user wanting to use a library, but what if you're an innovator? You're actually somebody who's doing something where there's really no good library out there. You're doing something new. If you're in a company, you're trying to beat out the competition. You don't want to just do the same thing as Google, unless you are Google. But if you're not Google, you don't want to do the same thing. You want to do something that actually is better than them, or whoever your competitor is, right? You don't want to just do the same old, or you're doing a problem that just doesn't fit into a standard library. What do? Suppose you're innovating beyond the libraries. Okay, well, I'm going to give you, again, an example. There's nothing special about this example, but if you like matrices, I mean, this is just a custom matrix structure, one that came up in my own work. But you see, this is what happens. People do some work, and then they have special structure, and the libraries are not built for these special structures. And so you can use these libraries, but you're not taking advantage of what you know about your own problem. And that's what people want to do. So I'm going to give you, again, an example. It's a bit of a contrived example. It did come up in my work. But suppose I have a matrix, an n by n matrix, a square matrix, that depends on only n numbers. And here's how it's going to happen. I'll give you this 3 by 3 example. I'm going to have a vector v that has 3 numbers, v1, v2, and v3. And I want to create the diagonal of v. That's what this looks like. And then the matrix the multiplication table, v times v transpose, which just means take all the products of v1, v2, v3 with v1, v2, 3. And I want to add them. All right, so this is my special matrix. Okay, it's built from n numbers, not n squared numbers. Right? Well, first of all, by the way, this is not a sparse matrix, because if you live in the linear algebra world, a sparse matrix is a matrix with a lot of zeros. But people really wouldn't want to call this a dense matrix either. It's really a structured matrix. I think that's the word people would say. It's structured. It's not just like any old n squared set of numbers. It's a structured matrix. So what do you do in Julia? You create a type. Okay, and so I'm going to create a supercomputing matrix, and it's going to be made out of a vector v. Okay, and my goal here is to never store n squared numbers. I just want to store n numbers because that would be crazy. So in Julia, there's a lot of punctuation here that might seem a little scary, but I want to make this work for very general numbers, not just integers and floats. I'd like this to be very general, and so I kind of made it a bit more general than maybe I needed to do. But what do you really want to do? Well, if A is a special supercomputing matrix, that's what I'm calling it, a supercomputing matrix, I want to get the size. Well, if V is length 3, then as a matrix, it's 3 by 3. And so even though I'm not going to store a 3 by 3 matrix, I can put the size as, the number of rows and number of columns as 3 by 3. And if I want to actually get an element, all I have to do is, if I'm on the diagonal, I have to pluck out this number. And on or off the diagonal, I have to compute this number. So you see, I'm spoofing being an n by n matrix. And you can see here is one of my matrices built from the vector 1, 10, 100. Right? And so you might be able to quickly check that if I subtract 1, 10, 100 on the diagonal, I get the multiplication table of 1, 10, 100 with itself. Now, you might say, oh, this is a 3 by 3 matrix. This is not just a 3 vector. And I'm going to tell you, no, not really, not stored in the computer. In Julia, you can type dump, and it'll show you that A is really stored as a 3 vector, not as a 3 by 3 matrix. Okay. Of course, if I wanted to, I could cast it as a matrix by typing matrix of A, and then I could see all 9 numbers being explicitly calculated and stored. So the message is, if you have a structure that doesn't need n squared storage, you have an n by n matrix that's based on n parameters, you could just store n parameters. Okay? And once again, this doesn't have to be linear algebra. This could be any machine learning example, any scientific example, any economic example, any commercial application, whatever it is you want, you can have that kind of storage, right? So now what I wanted to do, again, I'm a linear algebra guy. If the word eigensolver just scares you, don't worry about it. But let me tell you that I have made a special eigensolver for my matrix. And so I'm going to call it eigenmax to be consistent with the eigensolvers out there. So I want the largest eigenvalue. And you can see that I can calculate the largest eigenvalue here with my own special purpose code. And I can compare it with the LAPACK library. And look, I got the same answer. Yay, that makes me happy. All right. So again, you know, when I was in the supercomputing audience, when I was in the conference, sorry, when I was on stage, I knew that in the audience there were people who know linear algebra way better than me. And then there were lots of people who hate linear algebra, never took linear algebra, forgot their linear algebra, whatever. Didn't matter. The point was that I have library software over here that will calculate the answer. And I have my own custom software that will do the answer faster and with less storage. Okay, I have a little Newton method here that'll work. Okay, great. So I can take advantage of my, but what I really wanted to demonstrate for this audience is that I can go heterogeneous. And so I'm going to sort of run some of these things just to get these started. So what I'm going to do is run the same code. I want to run it on a GPU. So there, in Julia, we have this thing called a CUDA array, which lets you create a GPU version of the code. Okay, and then I'm going to have a distributed version of the same code. Now the thing is, this warning maybe could go away, but it does tell you that scalar operations are slow, but that's fine. Here, let's get rid of that. What this says is this matrix, this 3 by 3 matrix, it's small, but later we're going to do a big one. This 3 by 3 matrix is living on a GPU now. Oh, and this one, distribute, is living on a parallel computer now. That's great. And of course, if I want to reconvert it back, I could cast it back as a matrix, and then it puts it back, you know, on the front end computer. But let's do the all-important comparison of timings, all right? And so now what I'm going to do is I'm going to take n to be 4 million, right? And I couldn't even put a 4 million by 4 million computer on my machine. So here what I'm going to do is I'm going to set n to be 4 million, and I'm just going to create 4 million random numbers. There's nothing special about these random numbers. They're normally distributed, but that's not important. Here's the first bunch of them, and then Julia displays it with ... and here's the last bunch. And so now again, we're going to create a 4 million by 4 million, we're going to spoof it. It's not really 4 million by 4 million, but it's going to be the structure. And then there it is, the top left and the bottom right. And let me also distribute it and put it on a GPU. Okay, and here it is, I'm going to time it on the front end, and it looks like it's about 460 milliseconds. Okay, I'm also going to time it on 4 processors, and it's not a very good parallel machine. I didn't really get a 4-fold speed up, but I got some speed up. That's nice. Okay, and now I'm going to do it on a GPU. Let me just get it. And oh, look at that. That's really nice. This was half a second on like a laptop, and this was a little bit better on the distributed machine, but it's only 10 milliseconds on the GPU, right? And by the way, I did not write any new code. It was the same code. It was my eigenmax, my personal eigenmax. I'll show you, I'll go back up if it's not too freaky to see it all again. Whatever is in here, it's doing some kind of Newton's method. I don't know what it's doing. I mean, I do know, but it doesn't matter what it's doing. This code is running on all of these platforms. And this is the kind of thing that we're trying to do in the Julia community, to get as much of this sort of thing to happen with as many kinds of codes as possible, right? We're not there yet, but we're getting there, and we're doing it one by one. And we're trying to get the dream of high performance computing to be that you can basically write codes that more or less will run everywhere with performance. So how is it we can do this when everybody else failed? Or I don't know if people failed, but what are Julia's advantages? Well, the big advantage, and once again, it's not new, is the concept of abstraction. So you may have noticed that I use abstractions in 2 ways so far in this fun little demo. In one case, I said that a data structure could be a mathematical matrix. I used n storage, and I used it as if it was an ordinary matrix without any problem, right? It wasn't really a matrix. It wasn't an n by n storage structure, but in my mind it was a matrix. And as an abstraction, it was a matrix, and the code didn't stop me. It worked just fine. And then the other abstraction is that where a matrix is stored and runs was hardly noticed. It could be serial on a laptop. It could be distributed on a parallel computer. It could be GPU, right? Because Julia has good abstractions, the software can carry through and run, doing the right specialized software at the right times. But from the point of view of the highest level user, you don't have to know. So why could you do this with Julia? Well, that's a long story, and we wrote a paper on this. But some of the things that are valuable about Julia is that it has well-designed abstractions, has something called multiple dispatch, which I guess we're not really getting into today. It compiles to GPU at multiple levels, not just at the CUDA level. Plays nicely with Python. If you have legacy codes in Fortran or C++, you can call them in and work. You don't have to like rewrite your code. Some people worry about that. Do I have to rewrite my code? I like Julia, but do I have to rewrite my code? And the answer is no, you don't. If you want to know more, there's this paper. You can Google it, Julia, Fresh Approach to Numerical Computing. Here it is online if you want to look at it. And so we've written down exactly why it is that one can be able to do all of these sorts of things with Julia. Okay, so let me go back to my slides. I hope you kind of appreciated the point that language matters, and with the right language and a lot of hard work, we can really build a high-performance language that works in heterogeneous environments, even new environments that we haven't imagined yet, new kinds of computers that don't exist yet. We'd like to be able to imagine that Julia would be ready for those computers as well. I've got a few other examples. I don't know whether Matt showed them to you or not, but I don't think I need to go on them too much. I bet Matt showed off Celeste.
I did not, actually.
Did not? Oh, okay, well then maybe I should mention Celeste briefly.
It'd be good.
So this is a big machine learning example that ran at a petascale, and so just there are these supercomputing words. Maybe they're worth explaining. So on supercomputers, in the old days, we used to talk about machines running at a megaflop, which means a million floating point operations, like a million pluses and multiplies a second. Right? That was a megaflop. And then we got to a gigaflop, which was 1,000 million or a billion of those things. Right? And then we got to a teraflop, which was 1,000 billion of those things. And then we got to a petaflop, which was 1,000-fold more. Is that 10 to the 15th? I kind of lose track. But in any event, these are the, and then people are talking about exascale, which I think is 10 to the 18th flops a second. And so computers keep getting faster and faster and faster. And this was an example that was run in cooperation with the Berkeley National Lab. And they achieved petascale computing. And it is the actual first example of a high-performance language hitting the petascale club. And I think we're still the only member. I think Julia is still the only high-level language that has ever been clocked at running at a petascale. And so this was mapping, the application was mapping the skies. They have these telescopes that pick up all these points of light, and then you want to try to identify what you're looking at. And so this machine learning example was figuring it all out.
The part that I like to talk about with that example, Ellen, if you don't mind interjecting just a moment. This ran on what was at the time, I believe, the 5th fastest supercomputer in the world.
Yeah, Cori.
The Cori. And one of the challenges with supercomputers is that you don't always have access to it. And so the other thing is when you write against a supercomputer in a low-level language, well, that tends to be tailored very specifically for that particular supercomputer, those interconnects, those things. And so the beauty of a high-level language is that, well, you just express your algorithm. And in fact, after we lost access to the cluster, because of course you don't have access to a cluster like that very frequently, we took the same code base and ported it to Microsoft Azure, the cloud-based environment where you can spin up your own nodes and get things going. And it took just a day's worth of work to get the highly specialized code that ran at a petascale on a supercomputer to run on cloud computing infrastructure, because that's the infrastructure that us everyday people have access to. And so that's how we continued iterating on it after we lost access to the supercomputer, the power of a high-level language.
And I guess the moral is that's a good story. The moral is, and people say this all the time in the Julia world, It's tell us what you want to compute, not how you want to compute it, right? People get lost in the difference between what you really want and how you're going to do it. Because in many computer languages, you're stuck with figuring out how to do it. A little bit about Intel and its new architectures. I think I'm going to skip this slide other to say that, that Intel's been a great supporter for us and has helped us work on their processors and their new to come out GPUs. I've got some climate modeling people that we work with. And here the story is kind of fun because there are some folks at MIT and Caltech who are building the next best climate model and ocean models. And some of the MIT guys, and also people from the Naval Postgraduate School, I should mention, and some of the MIT guys, they came over to my office, they sat on my couch, I have a couch right here in my office, and they said, hey, Alan, we want to use Julia, no more of this Fortran stuff. Don't talk us out of it. But they said, they gave me a condition. They said that the code, they're going to give you 3 weeks, and they gave like a small piece of their code, and they want to see if they can get like within can I get within a factor of 3 performance of what their best people can get? Well, we got the code 3 weeks later, we showed them, and we got that factor of 3. Guess what? It was 3 times faster than their best codes. Why? Because people get lost in the weeds when they performance engineer. And if you can actually put it down at the lower level, it gets compounded all the way up. And so it works so much better. We like to say code is the new math. You don't code the math, code is the math. Julia code actually looks like the math. So if you speak these weird symbols, you actually recognize what these things look like. This was the climate model. And then there's how it actually works under the hood. I'm going to run out of time, but I just wanted to show you these slides. And you could look at Tim Bizard's thesis, for example, if you want to learn more about this thing. But basically, Julia is compiling to the GPUs at multiple levels so that we can get advantage of code reuse at many, many, many different levels. So here are some of the active areas of Julia. But let me kind of conclude because I'm at the hour and I promised to finish at 1 o'clock and I also have meetings to go to, and maybe you do too. I wanted to make clear that Julia is a high-level parallel computing language and Julia will solve the great HPC language problem, okay? And if you want to participate, you can always go to Discourse, you can go to Slack, you can email the Julia Lab. Obviously, you're not here with me in person, otherwise you can come talk to me. But we want people to participate. We want more and more people. We want to grow this ecosystem of high-performance Julia. And let me finish with one more quote that's not on my slides, but I could type it maybe, which a quote that I like, maybe just as a last thing I might mention. If I can do this. Oh, I can't do this. Why can't I do this? I'll just put it in here then. Yeah, can I insert text? Insert. Hard to do these things live. I just want to type some words. I want to say humans compose when software composes. Because this is something we've seen over and over, that people do work together and we actually get code reused. Somebody writes a code for purpose A and then it gets used in B. Why? Because Julia's designed that way, that the pieces can't fit together. And so I really do like the statement that humans compose when software composes. And so my temptation is to try to finish with that little quote. All right, let me thank everybody for participating and please become Julia people. There are many out there and maybe there'll be many more very soon. So please join the fun.
Yes, thank you, Alan, and thank you all for joining us. I hope this hour has been informative and helpful for you, and I really do hope to see all of you around. Go check it out, download Julia, try some of these things out.
Oh, come to JuliaCon in Lisbon this July.
Yes, we're very excited to head to Portugal this year. So hope to see you there.
All right, bye everybody.
All right, bye-bye.